All right, guys, in this video, we are going to cover the second half of the section 1.4 with the building functions from functions. So in the last video, we talked about composite functions. If that's what you need to see a video on, then make sure that you go back and watch part A. But in this video, we're going to talk about relations. And relations are just any kind of relationship between X and Y. They don't have to be functions. So if you guys remember back to your algebra classes, when you were telling if something was a function, a lot of times you would use something called the vertical line test. If you had a parabola, you were able to tell that that was a function because if you dropped a vertical line down it, it only hits in one location. Whereas if you had a sideways parabola and you drop a vertical line, it hits twice because not every single input had one output. If I look at the X value where this is, that X value actually had two different outputs, two different Y values. And so that made it not a function. So sometimes relations are functions, but not always. Otherwise, we would never end up with things like circles or sideways parabolas. So most of the time we try to stick to functions, but sometimes we get different things. This is what you're seeing here is a relation, and they are asking if these pairs, if these coordinates exist in this relation. And then we have to check, is the relation a function or not? So what we're going to do is just check these ordered pairs by plugging them into the function. So if you think about the points, I have the point 2, -5. Just remember that every single point is giving you an X value and a Y value. So when I see this, 2, -5, I'm seeing an X value of 2, and I'm seeing a Y value of -5, right? So what I can do is I can take those and just plug them in to this equation. So I would have 2, right, the X value, 2 squared times the Y value, -5, plus this Y value of -5 squared. And what we're going to ask ourselves is, does this equal 5? Okay, so you're going to go in and you're going to work through this. 2 squared is 4, and 4 times -5 is a -20, right? Then we have plus -5 squared. -5 squared is 25. Again, you're asking yourself, does this equal 5, right? All right, -20 plus 25, that makes 5. And does 5 equal 5? Why, yes, it does, right? And that means that that point is in the relation, okay? So then I'm going to check the next point. And I would encourage you guys to pause the video, try plugging in the next point, and then actually try plugging in the next 2 points and come back once you've tried it to see if you did it right, okay? All right, so we're going to plug in, again, we're going to plug in the X and the Y. So I'm going to plug this in as 1 squared times 3 plus 3 squared and ask, does this equal 5, right? Well, when you work through this one, 1 squared is 1 times 3 is 3. And then 3 squared over here is 9. 9 plus 3 is 12, and that is not the same as 5. So that point is not in the relation. All right, the next point I'm supposed to be checking is 2, 1. Plug that in. That is 2 squared times 1 plus 1 squared. Does that equal 5? So 2 squared is 4 times 1 is 4 still. Over here, 1 squared is 1. 4 plus 1 is 5. Does 5 equal 5? Yes, it does. So we had 2 of these points were in our relation. So to answer the question, the points 2, -5 and 2, 1 are in the relation. Okay? But that doesn't answer the whole question because the last thing says, is the relation a function? So we need to remember functions, right? If you were to graph this, I'm just going to make a little grid right here. If I were to graph these points at 2, 1, and 2, -1, 2, 3, 4, 5, that would be here and here. And I want you to think about that vertical line test. If you drop that down, that hits both this point and this point. So the answer is this is not a function. And that's because not every input has only one output. Okay? I have to squish that down there. But not every input has only one output. Okay? All right, that was example 5. Now, y'all, we're going to talk about implicit functions. Implicit functions are functions that you can't necessarily just write it as like y equals and then get an answer. Like you can't just write one variable in terms of another. You can't just use one equation to do that. You may end up having to use multiple, which is interesting, but a thing. So we're going to look here. You see example 6, they said describe the graph of the relation x squared plus 2xy plus y squared equals 1. So what we're going to do, because not every single calculator allows you to actually type stuff in that way, especially some of the older ones don't necessarily have a feature that lets you type things in that way. They always want everything to say y equals. What we're going to do is try to rearrange this. And I know I said implicit functions don't let you just write stuff in that term, but we are able to kind of manipulate this to work. So I'm going to show you something that's pretty, maybe different than what you would instinctually do, but this is how we would go about it. What we're going to do is try to force ourselves to write this as y equals and see if there's a way to get y by itself. All right, so this is kind of gross, okay? And some of you guys might think about factoring, but you may not always think to factor the way that I'm thinking of. So what I see when I look at this is I actually see a perfect square trinomial. It factors really pretty. If you don't believe me, just watch, okay? So this first one is the first term in each of these binomials needs to multiply to be x squared, meaning this needs to be x and x, right? Now think about it. The last terms need to multiply to be y squared, meaning it would need to be y and y. These both have pluses, meaning that these would both have to have pluses. There's no way around it. They're both positive. So what I want you to do is double check and make sure that works. X times x, x squared, right? So FOIL, right? X times x, x squared. Now look, outside times outside. X times y is 1 xy. Now if I do inside times inside, I get another xy. So that gives you 2 xy's, like that middle term. Last times last, y times y gives you y squared. So that is factored. And look how cool this is, guys. We get x plus y, and you can rewrite this as x plus y squared. And that allows you to do another fun trick, right? If I was trying to get y by itself, right now it's stuck inside those parentheses, but there's a cool trick. But when we have perfect squares, you can square root both sides, and that will get rid of that perfect square. So really, this is x plus y on its own. And then the square root of 1, remember we have to always put plus or minus, but the square root of 1 is 1. We have an equation here, and now it's kind of split into two. We have one equation where it says x plus y equals 1. The other is x plus y equals negative 1. So I'm going to write those out separately. X plus y equals 1, or x plus y equals negative 1. And then I solve this by getting y by itself. Subtract your x on both sides. Gives me negative x plus 1. On the other one, if I subtract x on both sides, we get y equals negative x minus 1. And you might be looking at this and saying, oh my gosh, like what's the point of this? We just got two equations. I thought I was supposed to be graphing this ugly thing, right? So here's the cool thing. What we're going to do is on our NumWorks calculators, I'm going to show you what this looks like, okay? We're going to graph this together. So if you are working with a NumWorks, again, that app is free, so you're always welcome to download that and work with it. But on my NumWorks calculator, I'm going to go to the grapher, And we're going to add an element. But instead of opening up a function, we're going to open up this empty thing. And it allows me to type anything that I want to. So what we're going to do is just type this whole thing in, including the equals 1. So this would be x squared. Then we're going to have plus 2x. And then the way we get a y on here, you say alpha 3. Alpha 3 will put a y on the screen, okay? All right, then we have plus y. So I need alpha 3 again, squared. Then I need this to say equals 1. So we're going to hit shift pi. It gives us an equals 1. Hit OK. And it's entered that relation in. It's not a function, but it does enter that relation in so that we can see what the graph looks like. If you do this on an 84, sometimes it doesn't work out so well, some of the older ones especially. All right, go to graph and look at what it graphs. We inputted this ugly equation right here, right, with all the squares and stuff. But look what it graphed. It graphed 2 lines. What did we get when we solved this? 2 linear equations. What do you know about these lines on the graph? They're parallel, right? And they've got a negative slope. Well, look here. On our lines, they have the same slope, -1 in front of that x, right? That's your slope, -1. It's a negative slope, just like our graph shows us going downhill. So what these two things do is they give you the graph, or they give you the equation of the graphs that this thing puts, right? That ugly equation graphs 2 lines. That's not a function. If you drop a line, a vertical line, it's going to hit twice no matter where you drop that line. And this is showing you how you're able to actually get the equations for those lines using algebra. Okay? All right, moving on. We got one more scenario. We're going to talk about piecewise defined functions. Piecewise functions are talking about graphs that you piece together. That's it. Taking functions, piecing them together, and making graphs. And to me, I think of them kind of as puzzles. I think they're kind of cool, actually. You just have to pay attention to what the x values are for each part. But as long as you see what the x values are for each part of your graph, then you should be able just to graph this without much of a problem. So what we're going to do here is I've got this function. Again, this is example 7. We're seeing this whole scenario right here where they said as long as x is less than -1, then my x, we're going to use the function x squared. If we plug in an x that is between -1 and 1, right, also including -1, right, you see that less than or equals to. If you plug in an x from this little range, then you're going to use this equation. If I plug in an x that's from this little domain, I'm going to use this function. So it just depends on what x you're plugging in to know what the graph is going to look like in that area. I'm going to scooch this over just so that I can put my paper over here and try to give you a nice little graph. So I'm going to set up a little graph grid right here. We're going to go 1, 2, 3, 1, 2, 3. We're going to go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't have to be equally spaced. It's okay. But we are going to make ourselves a little XY table because I think that will help. We're going to pick values to plug in. I would like to pick values that are from each of the different domains so we get a full picture. So I see this first one where they said x is less than -1. I'm going to make sure to plug in some values where x is less than -1. So it doesn't really matter what you plug in, just plug in a couple so we can see the picture on that side. I'm just going to go with like -3 and -2, okay? You could plug in fractions if you wanted, but I'm just going to go with these. And if you plug in a -3, right, that's less than -1, it goes into the top equation. -3 squared is a +9. That would be my output. If you plug in a -2, again, -2 is less than -1, so it's going to go into that top equation. -2 squared is 4, so that's going to be the output. But I want you to think, if I keep going on this trend, I plugged in a -3, -2, what about a -1? Well, that doesn't go into the top one because the top one's only for if x is less than -1. But if I plug in a -1, I'm going to have to move on to this next function, right? This is the one that says x could be equal to -1. This is if x is between -1 and 1, but it could also include -1. Plug that into the middle equation, which is the absolute value. If I plug in a -1 to the absolute value, I'm going to get absolute value of -1, which is +1. Let's pause real quick and see what this looks like on the graph just so far, okay? Before I get too far ahead of myself. So we plugged in a 3 and got 9, okay? Something like that. All right, if I plugged in a 2, got 4. 1, 2, 3, 4, something like that. If you plugged in a 1, you got a 1. Now I want you to think, if I'd also plugged a 1 into the top one, -1 squared is 1, I still would have had the same output. This is quadratic on this side, so it's kind of scooped. But what happens in the middle? Well, if I keep going and plugging more values in, if I plug in a 0, 0 is in this little domain, so I'm going to use that absolute value again. Absolute value of 0 is 0, which means I would get a point here at my origin. But you need to remember what the shape of absolute value is. Otherwise, you have to plug in more stuff. Absolute value should make a V shape, okay? So it should be kind of a sharp little V. It shouldn't be curved down here. So if your graph is looking bigger than mine, you got to make sure you're being very careful. This is going to be a sharp point, not a curve at the bottom. All right. Now, if I were to plug in a +1, right, that brings me into the next bracket of looking at integer. Okay, the integer function works the same. It always gives you an output of an integer. If I say integer x, we're going to, and I plug in a 1, it's going to be an output of a 1. It's always going to be that integer. Okay, this is going to go right back up, kind of a sharp. Again, we want that to look like a V in the middle. But here's how that integer function works. It is a step function. It's going to look like stairs. It gives you like a bunch of little segments. If I plugged in for that integer function, if I plugged in like a 1.5, my output is still going to be a 1. If I plug in like a 1.9, my output is still a 1. It does not get to be a 2 until I plug in a 2. And when I plug in a 2, my output will be a 2. So your output is always going to be an integer for an integer function. And that's what gives us that step type of behavior. So you're going to see here, it was always at that value of 1, then it's going to go up, and then get another stair step. I can put more of these points out here. It's just going to keep stepping up and up. Give you all these little segments. That's what the integer function looks like. Okay, so it's going to go up, over, kind of like that. Okay, so that's a piecewise function, guys. On one side, we had a parabola. Then it turned into absolute value. Then it turned into the integer function. So we pieced 3 different functions together to make our graph. Cool. All right, guys, that is it for this lesson, and I will see you in the next one. Good luck. Bye.